right. And the last speaker of today's session is Ali Vakilian, who will tell us how to beat classical streaming barriers using predictions.
Yeah, thanks, Peter. Okay, yeah, let me just go through it quickly. Yes, so I'm going to talk about building classical streaming algorithm using prediction. So it's basically learning augmented algorithm for a streaming problem. So first, let me describe the model. So in a streaming model, usually the whole idea is that the amount of memory that is available to the algorithm is much smaller than the size of the input stream that the algorithm needs to process. So more formally, we have a massively long data stream, A1 to A capital N, and the idea is to use a sublinear amount of space n to the alpha, where alpha is smaller than 1. And in most cases, what we are actually looking for is polylogarithmic in the size of in n. And we also want to have a small number of passes over the stream. Ideally, it's just one pass. And then at the end, we would like to be able to compute a given function f over this stream. It has been a widely studied domain, and you will see actually many talks in this conference, for instance, on this streaming model only. So what's the idea now that given the theme of this workshop for machine learning for algorithm, what if we want to have algorithm that use prediction, in particular streaming algorithm using prediction? So this is the classical pipeline of the algorithm. So we receive the input, and then a streaming algorithm does something on it and just spit out the output. But these days, we may have some extra information, and usually through the machine learning components or models that we have. It could be simple machine learning components. It could be a regressor, or a bit more advanced neural networks, or even just state-of-the-art models like the LLMs that we have access these days. And the idea is that we receive this prediction from these models. They're basically trained on the past data, and we want to be able to do something better on this new instance. This algorithmic prediction in general, and also called learning augmented algorithms. And my focus, as I mentioned, is on a streaming algorithm. So what's the promise of this line of research is that if this machine learning oracle provides a good advice or prediction, then we would like basically to have a better performance. We get closer to the optimum value. And the way, for the first part, I assume that we have access to this machine learning model is through an oracle that provides some prediction. But so this is the good part. This is where we can basically exploit the machine learning predictions. But at the same time, we don't want to be completely fooled by bad predictions. So in particular, if the machine learning oracle perform poorly, we still would like to be able to preserve the same worst case guarantees that we could have without using the prediction. So the first part is basically the consistency criteria, and the second one is the robustness criteria. So consistency, basically we are comparing to the actual opt when predictions are good, and the robustness saying that we should be able, we should remain comparable to the best worst case guarantee even if the prediction is poor. Okay, just before going through the actual material, so a useful resource here for this learning augmented algorithm is in this website, Algorithms with Prediction, that's a repository of the papers on this topic. In particular, I'm talking about the streaming, which is not, I'm doing justice on the whole topics that people have studied, in particular online algorithms or graph algorithm. And there have been lots of work on these topics as well. So I encourage, if you're interested in, just take a look at this website as well. Okay, so and then the outline of my talk is as follows. First, I will talk about streaming algorithm using learned oracle, which basically I describe, and then talk about a streaming algorithm with learned structures. And at the end, if I have time, I will talk about a streaming algorithm using a theoretical framework, which is called epsilon accurate predictions. Okay, so let's start with the learned oracle, and it's a joint work with Piotr and my other co-authors. and it's about basically frequency estimation problem. So in this problem, we are given a stream of items that arrive one by one, and we would like to have a one pass over the stream and using a sublinear amount of a space, which here is polylogarithmic in n, and then compute the frequency of items approximately. So it's not possible to compute them exactly if we want to use sublinear space, so this is basically the best we can hope for. So this is a very fundamental problem in data analysis. I mean, it can show up in many places in natural language processing, networking, database optimization. And it's a very fundamental problem. And it has been studied from the classical point of view, classical streaming algorithm point of view also a lot. And for instance, one successful approach is the hashing-based techniques. For instance, count mean and count sketch that have been developed for these type of problems. And they basically, what they're doing, they're hashing items as arrive into different hash tables, and then once the stream is over, they look at these hash tables and pick the best estimate among them. Okay, for instance, in count mean, we just simply hash the items in the tables, and since the item can only collide and basically the value that we see in each cell is only overestimating the actual frequency of an item, at the end we just look at the minimum of the estimates we receive from these hash tables. Okay, so our learning augmented algorithm for this frequency estimation is kind of simple once we have the prediction model. And what we did was we trained a machine learning oracle that would tell us basically whether an element is a frequent one or not. So we call it heavy hitter oracle. And then once we have this machine learning oracle, once we are processing the next item in the stream, we just first feed it to the oracle and ask whether it's a frequent item or not. And basically, depending on the answer of the oracle, we are going to treat the item differently. If it's frequent, then we will count its frequency exactly. So we allocate a different word of memory for that to count its frequency exactly. And otherwise, if it's labeled as non-frequent, we will feed it to the sketching algorithm. Let's say count mean or count sketch, just a regular sketching algorithm. So in high level, why this is going to help us, because collision with frequent item is actually very costly in these count mean count sketch type of algorithm. Because once they collide with an item, that item has to pay that error, basically the error corresponding to their frequency. So it would help, I mean, in two ways when we are separating them from the rest of the items. So other items do not have to pay a lot in their error, frequency error, and the frequent items themselves also will benefit from it. So that's basically the high level idea. And actually, we also show that even if we know the actual distribution, I mean the frequency, this is the best thing we can do to separate the high frequency items from the rest. Okay, and I mean, in terms of consistency, we show that if the distribution of item is Zipfian, then this learned sketch is actually provably doing better than the count mean or count sketch. For instance, this is one example. This is the expected error for the count mean, and the second row is expected error of the learned version of count mean. And we also do some further sketching with this learned idea, and that got the best expected error. So that's good. I mean, we have this consistency. And for the robustness, I mean, the part that is helping us is that even if the predictions are useless, since we are still using a sketching algorithm as a backup, we will attain the worst case guarantee that that sketching algorithm is going to achieve. So that part is okay. So we will have also some worst case guarantee comparable to the best existing algorithm without predictions. And also, I mean, what was important for us was that empirically this learned count mean also works very well. I mean, it reduces almost by 50% reduces the estimated frequency error by almost 50%. So, and this is actually the more details on how it performs. So here, the blue and orange one are, the blue one basically is the count winner count sketch. The orange one is the count winner count sketch with lookup table. And lookup table, what it does is that basically look at the first, a small portion of the stream and then try to memorize the heavy hitter. So it's kind of learning itself, right? It's try to see what are the heavy hitters in the first, let's say, 1/epsilon fraction of the stream, and then treat them as a heavy hitter. And then the red one is the learned count sketch or count mean using the neural network implementation. So we had this heavy hitter oracle, use it by RNN. This is basically the spec of that network. And the green one is our algorithm when we have access to an ideal oracle that exactly tell us, who are frequent and who are not. And one interesting point is that actually, lookup table tends to memorize the heavy hitter, but let's say even from the past or anything. But this oracle, learned oracle, they apparently learn some structure about the heavy hitter. So this basically plots show that there's something that can be learned about the structure or pattern of the heavy hitters for these applications that we consider, for instance, the network traffic or the search queries. For instance, it will understand that if the query is smaller, then it's more likely that it's for instance, be frequent. So this is something that is not achieved by just a lookup table. Yes? No. In our oracle, we learn from the past, the day or traffic or yeah. But the lookup table look at the same stream. That's a good question. Okay, and yeah, that was one line of research. I'm using this oracle and how we can get better streaming algorithm. And there has been subsequent work on that. Getting better tail bounds, looking at this problem in a sliding window stream. Or, I talk about the hashing-based algorithm for frequency estimation, but there are also more deterministic algorithm like Misra-Grice algorithm. They can also be equipped with this learning augmented techniques. And also this heavy hitter type oracle also has been used in other problems in a streaming like triangle or 4-cycle counting. So there have been lots of interesting questions still there. For instance, people have been looking at other frequency vector problem in streaming. There has been this work by Jiang, Li, Lin, Ruan, and Woodruff. They were looking at distinct element, FB moment, or cascaded node. That's a very fundamental problem in streaming, and they show that we can basically break all the existing barrier in the classical streaming using these prediction models. Okay, so just a few questions here. So most of the theory bounds that we know for consistency part in this frequency type estimation problem in the streaming are for Zipfian or Zipfian-like distribution. So what about other distribution? For instance, some other structure like tail distribution, or ideally if we can just give an arbitrary distribution, if we can say something. This is still, we don't know how to show. And the other point is about the parsimonious setting. So far I assume asking for prediction is cheap and has no cost, but in reality, it could be very costly. If you work with this API and have used token, they actually cost you something. So then it's useful, to come up with some algorithm that just rarely use this prediction. And this is basically the second line of research, parsimonious setting. So if I just want to do it constant many, for instance, prediction, what can I achieve? And the other one is using multiple prediction to design a good algorithm, streaming algorithm, which then good here means to being comparable to the best existing predictor. So this has been studied in online setting more, but for streaming we don't have. I don't know of any work that considering these multiple predictions in a streaming setting. Okay, so now let me switch to the second part, which is the learned structure. So in the first, we try to identify a compact, learnable prediction. For instance, in the frequency estimation, we said, okay, heavy heater could be a good predictors for our problem. So it requires some work, to basically identify such a thing and then try to see if it's actually learnable. And the third part that I didn't talk about and Nina mentioned is actually try to show that theoretically that it's also learnable. So that's one paradigm, but the second one is try to basically learn some structure in the algorithm itself, and then basically, yeah, using machine learning in that sense. So, and that basically here means that try to replace some sort of the randomness in the algorithms with the machine learning. So replace the random bits with the learned bits. And one good candidate for showing that is basically looking at the sketching algorithm. So a sketching algorithm, what the general framework is doing is as follows. So we have a high dimensional data. It could be a vector, it's a matrix, and so on. So it's basically in the sketching we compress the data, but by multiplying it with the sketching matrix S. Okay, so we multiply S by our data, and then we will have a low dimensional data, which is going to be good enough for our problem that we are trying to solve. And usually, after this is sketching. If the size of data is D, this sketching is of, let's say, size log D. So it's considerably smaller. And then the idea is that, this is preserving basically the structure that we need to solve the problem. So we only need to try to solve the problem on S times X rather than X itself. And it would improve both the running time and space complexity and so on. But here again, I'm focusing on the streaming and would like to consider the space complexity. It's a very powerful framework. It has, some examples are dimensionality reduction, and it has also, wide application in numerical linear algebra, like in regression, low-rank approximation, and so on. And in particular, I'm going to consider low-rank approximation to describe one of the results that we have here. So in low-rank approximation, we are given a matrix A and a rank parameter K, and the goal is to find the best rank K matrix that approximate a matrix A in terms of, let's say, Frobenius norm error. So this is the definition. This is a very basic problem, and in fact, we know that the singular value decomposition is going to solve this problem optimally. So this is very good. It's polynomial time optimal, but the runtime and the space is not that useful. In particular, if you look at it in the big data scheme. So the running time, for instance, is the minimum of n times d squared, or n squared d, and the space is n times d. So this is impractical in many cases. So people have then tried to study the approximate version of this problem. So instead of finding the best rank K, we are okay if you find some A prime whose Frobenius norm error difference from the actual A is within 1 plus epsilon times the best Frobenius norm error that's possible. Then, this is A prime is still quite good rank A approximation of the matrix. But at the same time, now there are more efficient algorithms. In particular, there are sketching-based algorithms first introduced by Sarles and Clarkson and Woodruff. And what they proposed was that if you just multiply, as I mentioned, just multiply sketch matrix A by your matrix A, then you can just try to run SVD type algorithm on S times A, and that would give you a 1 plus epsilon approximate solution, but now it's much faster and consume less memory. So in particular, it's very useful for a streaming setting because this sketching algorithm can be easily implemented in a streaming setting. So once, let's say in a streaming for the matrix processing is like you will receive updates to the columns of your matrix or to the rows of your matrix. But if you're working on a sketching algorithm, what you need to keep is just some sketch matrix, let's say R times A. And that updates, when that update arrives, you can easily compute how it would affect the R times A. So that's streaming friendly in a sense. And I mentioned this algorithm by Solis and Clarkson Woodruff. What they do is as follows. So they pick a random sketching matrix, and this random could be there are many different options for that. But let's say, I pick some random matrix R, and it has, um, the number of rows is usually k over epsilon. I guess that the best is about that, k over epsilon. And as I mentioned, this is streaming friendly, but you can easily compute over the stream. But the main part is that now to compute the 1 plus epsilon approximate rank K matrix B, you can run their algorithm, and they only need to basically keep track of R times A, which now you only requires n plus D times M rather than n times D. So it's basically improves over n times D of just the vanilla SVD. And the same phenomenon also for the running time is the case also. Okay. So this is pretty good. Even just using this randomness, we can improve the space complexity and running time a lot. But now our hope is that what if we try to replace this randomness by learned bits? So basically, what we are going to do, we look at this algorithm by Solis and Clarkson Woodruff. Basically they pick a random matrix R and then run basically the following algorithm. They compute R times A, then run SVD on RA, and then compute a V transpose, where V is basically the singular value decomposition of R times A appear in that, the right singular value. And then we return AV transpose rank K times V. Okay, so this is some algorithm. So to make it into the learning scheme framework, instead of picking a random matrix R, we try to learn a matrix R, which is going to be more efficient for the class of matrices that we have in mind. So hopefully the idea is the following. So we are trying to processing a family of matrices that are somewhat relevant. So they have some similar structure. And we hope that maybe if we replace the learned matrix, replace the random matrix with the learned matrix, that will perform better. So basically, this is what defined as learned sketch S. So it's going to have smaller number of rows. This is what we hope to achieve. And still, we are going to run the same SCW algorithm, and then we are trying to basically learn the best S for that algorithm. So basically, we have a training set. We are trying to minimize S, so pick S that minimize the expected error over these training matrices. Okay, so there are some challenges on how we can train it and what we should do about it, but let's forget about that. What we have actually captured in our paper, if you're interested in. But the bottom line is that we show that for the data sets that have a collection of matrices that are relevant, actually the empirical recovery of this learned sketch is much better than the randomized sketch. So, and this is not surprising. If they are somewhat related and we are doing some learning, this is what is expected to happen. And yeah. Okay. So what's that deep sketch? I don't know. Oh, okay. Oh, neural network. Okay. Yeah, I don't know about that. Let's maybe talk about it. Yeah. Okay, yeah, so these are the plots. So when we pick the learned one, this is performed better than the random one. Either you pick the sparse random matrix or the dense random matrix. This is performed much better than both. And in particular, just to give you some sense, this is the error, the empirical error, when we are using a learned sketch and when we are using the random sketch of the same size. Okay. Okay, so this is good. This is showing us that empirically we can do better, right? But we always, we also always talk about this robustness and the fact that we don't want to be screwed by these machine learning predictions. So how we can handle it here? And the idea was somewhat simple. So we just say, okay, you can just combine a random matrix with the learned matrix, and you will get the basically a reasonable performance. So we show that, I mean, empirically you get a reasonable performance. I mean, this is what we observe in all of the experiments that we did. But more importantly, we can show some sketch monotonicity lemma. So meaning that if you run these SCW algorithms, when combine R and S, the two sketching metrics together, the error would be less than the minimum of the error of the running SCW by R only or by S only. Okay, and this is, I mean, if you think about this algorithm, this is not it's not hard to see it, but the important fact is that, I mean, not all algorithms have this property. For instance, there are some algorithms, if I'm not wrong, by Michael Cohen, Musco, and Musco, where they first find some good direction of the matrix and then project on that and then do some algorithm, something on top of that. So if you follow that line of basically algorithm, then the monotonicity doesn't really exist, because once you add more matrix, I mean, you may change the direction significantly. So this is not true for all existing algorithms. So there are some algorithms that satisfy this property, and these Sarlos and Clarkson-Woodruff are one of those. Okay, sounds good. But let me see how much time I have. Okay. So one thing is that, I mean, I here kind of insist on having learned the sketch, but one could ask, okay, maybe why not just have an end-to-end algorithm, right? So I have a low-rank approximation. Now that you are trying to learn the sketch matrix, why not just to learn the whole algorithm? So there are still some advantages of having the sketching framework. So one is that if we follow the end-to-end, I mean, we don't know about the guarantee, right? And at the end, we need to test it to make sure, I mean, it's a good, let's say, rank K approximation, or if it's actually a rank K, for instance, solution. There's some difficulty on that, but this construction is valid, I mean, as we are producing it, because the way that we have this sketching algorithm, we are making sure that it's a low rank, and they have certain, let's say, error at most. No test is needed, basically. So the second one, which is more important, is that the linearity is preserved. So then maybe, I mean, these linear sketches are useful because you can compose them, they're mergeable. So there are certain properties that are preserved under these sketching techniques. And the last one is the few parameters are needed then to learn, rather than the whole end-to-end algorithm. That's in particular useful if you want later to argue about some sample efficient algorithm or some provable guarantee for the learned part as well. That we have some sort of provable guarantee, generalization guarantee for some restricted, I mean, class of matrices. So this is then much easier when you are dealing with the sketching framework rather than the end-to-end algorithm. Okay, so the last part is epsilon accurate prediction. That actually, I'm just going over it very quickly, but luckily we have one poster tomorrow which is on this topic, so I encourage you to go to that poster. So yeah, but the idea is as follows. So we assume that we can present the solution by some 0, 1, or -1 and 1 labels. So basically, the solution can be described as labeling some, let's say, vertices or points in the input. So let's say, I mean, x star is some vector -1 to 1 to the n, and then the oracle also provides some labeling, some predictions of this optimal labeling. But we assume that, and this is the critical point, is that these labels are independently correct with probability half plus epsilon. So basically, just barely better than a random guess, but they are independently correct. So, for instance, to give some idea, I mean, for instance, max cut can be seen as one of can fit this framework. So basically, the points in, let's say we want to find a bipartition, points are either in S or T, right? So let's say S is +1 and T is -1. And so we want to find the bipartition such that the number of edges that are between these two parts is maximum. Okay. Then basically the prediction could be whether a vertex V belongs to set S or not. Or you can think of a maximum independent set. So we have, again, I mean, the prediction can say whether a vertex belongs to a maximum independent set or not. So that's, again, fit this framework, and actually there have been some work on both of these problems. So yeah, sure. Yeah, that's a very strong assumption. Exactly. Yeah, that's true. I agree. I mean, the independence problem is kind of a strong assumption, and yeah, I tried. I mean, it's hard to come up to basically get the independence, and so that's actually lead to an interesting question. I think that if we can design such algorithms, so right now our algorithm somewhat they need some pairwise independence, but in general, if we can, what we can show here, we are given a correlated predictions vector, what we can achieve. So that's still we don't know very well, but yeah, that's one part. I mean, one step, and then if we allow for correlation, then it's easier to learn such prediction. So yeah, definitely, that's an interesting question. Yeah, but okay, actually, I may try to skip these parts maybe since we are already out of time. Yeah, but I want to say what's the graph streaming. Basically, edges comes and arrive. I mean, or in dynamic stream, you can also delete edges. And the hope is that we want to have one pass, a small space, usually O tilde of number of vertices. Okay. And for the streaming max cut, basically, I mean, the way that it helps, I mean, we consider the estimation task. We only want to give you some estimated value of the max cut. So there is a trivial half approximation, just by counting the number of edges and returning half of it. It's a half approximation. And surprisingly, Kapralov and Krautun show that basically to get better than half, to get basically something like half plus epsilon, you need to have omega of n space. So basically that's the optimum you can do in the classical setting. But we show that if you're using this epsilon accurate prediction, you can get better than half plus epsilon using only poly 1 over epsilon words of space, or in dynamic streaming, poly of log n of 1 over epsilon space. Okay, so unfortunately, I don't have time to go over that, but the high level idea is kind of simple. Maybe just also give you what's the algorithm. So we say that one of these two candidate solutions are going to be half plus epsilon approximate. So either you follow the prediction on low degree vertices and then try to extend that solution with the high degree vertices in a greedy fashion. So whenever a new let's say high degree vertex arrive, you just try to decide which side to put that high degree vertex according to the number of edges that it has to to the currently constructed bipartition SNT. So it's basically greedy augmentation for the high degree. And the second solution is basically try to look at the cut between the low degree and high degree. So one of these two is half plus epsilon approximate solution. Okay. Yeah, so there are some challenges with the streaming implementation for sure, because we don't know a priori who are the high degree or low degree vertices. So we need to do some sort of sampling and also keep some sketching of the edges of the vertices to the other vertices. But I mean, they can be done. And then we extend actually this prediction to the constraint satisfaction problem. But let's skip that also. I would be happy to talk about them offline if you're interested in. In particular for the die cuts, I mean, if you just naively follow the algorithm I described, I mean, you get 1/4. But we know actually, for instance, there's a paper in this STOC today actually that they show you can get a half approximation even without prediction. So somewhat we should do something differently rather than just following the prediction. And then our idea was basically we try to write some system of linear equations, and by solving them, then we can get much better approximation for a CSP type problem. Okay, so and this is again about the question that Nina was also asking, are these predictions actually learnable? So I mean, it's learnable if you look at them locally. I mean, we can come up with some prediction that's half plus epsilon correct for all vertices, but to make them independent, that's actually challenging. And that also suggests that maybe we should try to, we should try to design algorithms that do not rely on independence. I mean, that would be very interesting if we can design algorithms that work with some sort of correlation prediction. That's an interesting open question. Okay, so yeah, exactly. I mean, these are many questions can be asked here. So if you want to extend the result to the weighted graph, so far it's only about the unweighted graph, for instance, for the max card or CSP instances even, or maximum independence set and so on. I mean, I didn't talk about that. And also about other problem in the streaming like maximum independence set. We still don't know what can be done. Okay, thank you all, and see you tomorrow.
Questions?
So yeah, this is related to the philosophy for training the graph length, right? So I think for offline space, you can argue by saying that I just use my entire graph algorithm model, or I think that I train offline more. For training, I think you could do it, right?
Concerned about the space of
yeah, because training was small space, so have you yeah.
But the hope is that, I mean, given that there are all these predictions, maybe you have some predictions that multi-purpose predictions so that can use different problems. Or, I mean, the hope is that the same prediction will be used for several instances. So you can also think about our customers. But yeah, in general, it's something that you could kind of control what is important. Try to also capture the space.
For the purpose of class visit, you have maybe we can brainstorm together or something, right? So, yeah.
Getting back to that special thing with me, you think, I think this one of the framework like in family, Bonds classroom, try to find one that best fits. Can you think of a way, is there a way like back out and objective function? So currently this independence you use for some purpose, if one could back that out with an objective function, then you could say, hey, can I find the hypothesis in my family that has the lowest loss of its objective function? Maybe that would be one way to do it.
So for example, when you have historical that just gives you different cases, so it's the input of your own network. So how do you tell them?
So just for assessment from traffic, so we need the network traffic from the past days.
So the whole thing is
Yeah, it's going. But for the next, for the tomorrow, I mean, then we use it for the traffic that we see tomorrow.
so there is some user trips in small level.
Yeah, but it could be different. For instance, I mean, we realize it's less of that. For instance, you bet that some traffic from Google and from heavy lots of traffic. So it's actually there something. When we terminally visualize the things, realizing there's something. And I think that is different.
Okay.
All right, so our wall is disappearing. So let's thank all the speakers and see you tomorrow.